All right, you guys, we have just a couple lessons left for this chapter. Today we're talking about hyperbolas. So I'm going to give you kind of a sketch up here about what a hyperbola actually looks like. Let's say that you have a graph that looks something like this. And a hyperbola, we've talked about it briefly in class. It's two parabolas which actually kind of go away from each other. So it could look something like so. And it continues left and right in both directions. You could also have a hyperbola that, if I could squeeze one in here, that goes up and down. Like this, and like this. Okay, so they're like symmetric, and they have a lot of qualities about them that we're about to talk about, but this is what hyperbolas are. I'm going to give you a little bit of time to copy down the definition. We'll talk about that in class as usual. And then all these boxes, I'm going to kind of talk through them. I'm going to use this handy dandy laser pointer to help you. And also, by the way, we're being joined in the background by Dave Matthews. You're welcome. Okay. As you're copying some of this stuff down, if I go too fast, then just pause the video, whatever, get it copied down, no big deal. But the H and the K for the center is the same. HK, this side is normal. This side you do have to be careful because the H is always with the X value, which is why I drew these arrows here. And the K is always with the Y value. So sometimes the Y squared is written first, and that's actually your K. So just kind of remember that, like when we did parabolas, they're going to be flip-flopped. And the way that the direction opens depends on which fraction is first. See how the y is first for the vertical one? That means it opens up and down. However, when the x is first over here on the horizontal side, that means it opens left and right. Okay? So if I go back up to my example that I was doing up at the top, this is a x squared minus y squared hyperbola because it goes left and right. And the bottom one here is y squared minus x squared hyperbola because it opens up and down. Okay, and the only difference between the hyperbola and the ellipse formula, just take note, is the negative sign. So that's something that's pretty important. Otherwise it looks exactly like an ellipse and it has a lot of the same qualities, so very, very similar. Another thing is for the vertices and the foci, we're just going to look at the graph for those. That's like your little formula type of thing, but we're going to use some common sense and we're going to look at the graph to be able to figure those out. So you do not have to memorize those formulas. We also do have two new vocab words, a transverse axis and a conjugate axis. So the transverse axis connects the vertices, that's what I wrote down here. And it connects it on both sides, so it's either side to side or it's up and down depending on whether y is first or x is first. And the conjugate axis is kind of like major and minor axis in a way for ellipses. There's a transverse and a conjugate for hyperbolas. Transverse connects the vertices. The conjugate connects the other 2 points. So we can do lengths for those axes as well. Okay, so one other thing, well, a couple other things I wanted to talk about under other notes down here. I'm going to zoom in so my writing's a little bit nicer. We do have a formula to find foci. To find foci. Remember for ellipses we did that Pythagorean theorem type of formula with a minus sign? Well, for hyperbolas we actually do a straight Pythagorean theorem. A squared plus b squared equals c squared. And then that c is where the foci are located away from the center. So once you find c, it's exactly the same way we did for ellipses. You start on the center and you count either up and down or left and right, whatever c is, to find where those foci are. So we'll do a couple graphs so that that makes a little bit more sense. So that's how to find the foci. Another really important thing, and somewhat confusing, not going to lie, the a squared is always first. And it's not necessarily always the bigger one, like it was for ellipses. Okay. So I'm going to actually zoom out so we can talk again about the a squared really quick. I'm going to look at the original formulas up at the top. So notice how for vertical and for horizontal, the a squared is first for both of them. Okay, so the a and the b still kind of do like flip-flop, but the a is not always the bigger one. That's only for ellipses, so it is a little bit confusing. For hyperbolas, the a squared is always under the first fraction, and it could be x or y, just depending, okay? So you got to kind of keep that straight, something you're going to have to memorize. And let's blast into this very first example here. Okay, so it starts out almost exactly the same way as the ellipse. I'm actually going to do this one first. I'm going to pretend like I'm graphing an ellipse actually, because the start is exactly the same as the ellipse. So let's talk about what the center for this would be. Center would be positive 3, comma 0 because of the h and the k. So I'm going to put a dot on 3, comma 0. That's so far exactly the way we've done an ellipse. This is about to get mind-blowing though, you guys. All right, and so underneath the x squared is 16. And so just like we were doing an ellipse, that would mean we would go left and right 4. So I'm going to do the same thing there. I'm going to put a dot here, and I'm going to go 4 this way, put a dot there. And same exact thing for the y. Underneath the y squared is 25. That means I'm going to go up and down square root of 25. So 5. 1, 2, 3, 4, 5. Put a dot here, and put a dot here. Now some teachers refer to these 5 points that we have on our graph right now as the shell. Right now what we have is a shell of an ellipse, and so far it's exactly the same as the ellipse. But what I'm going to do now, this is the crazy part, you guys. It's obviously not an ellipse. So what I'm going to do is I'm going to make a box out of these points, kind of like asymptotes. And I'm just going to box in these points, like I would be doing an ellipse, but I'm just making a box instead of an ellipse, okay? Here's the even more mind-blowing part. If you think back to when we did rational expressions and we put all those asymptotes all over our graph, well, hyperbolas have asymptotes as well. So I'm going to actually connect the corners of my box, and these are going to be the asymptotes that are going to hold my parabolas, or my hyperbola, if you will, in place. Okay? So now I have my asymptotes going through the corners, and what I'm going to do now is, since I have x first, that means my vertices for my two parabolas are going to be sideways. That means I'm going to use this point and this point. Okay, and so now all I have to do is the asymptotes act like a magnet, and it's going to attract my graph right towards it. So it's going to go this way with an arrow, and this way for an arrow, and the other side. And you guys, this is what is forming our hyperbolic, or our hyperbola shape. Okay, that is the hyperbola. So what do I do with the other 2 points? Nothing really, but there are some specific questions that I will be able to ask you about these 2 things. So let me go to number 1. We already got the center. So I could also ask you, what are the vertices? AKA, what are the points that we used to make our hyperbola? So those are the points that I outlined in blue. And those are exact values. So what are those points? -1, comma 0, and the other one is 7, comma 0. So that's that. Another thing I could ask is length of transverse axis. So remember, that connects the vertices. So I'll just do this. I'm going to use my laser pointer actually. That's this right here. How long is this segment right here? I believe it is 8 units long. So that's the length of the transverse. And then the length of the conjugate axis is the other one. So that's where these 2 vertices come into play. This is 10 units long. So that's my conjugate length. That's 10. Another thing I have to do now is figure out what the foci are. And so how I'm going to do that is I'm going to use a squared plus b squared equals c squared. I'm going to zoom over here a little bit. A squared plus b squared equals c squared. So remember, the a is the 16. The b squared is the 25. That means my c equals plus or minus radical 41. And so from there, what I'm going to do is I'm going to start on the center, and I'm going to count to the left radical 41 and to the right radical 41. So just for an easy decimal, 41 is in between 36 and 49. So it's, when I square root it, it's somewhere between 6 and 7. So I'll just do 6.5 just because it'll be easy to graph that way. So I'm going to start on the center. So starting here and counting over 6.5. So I'm going to put a dot right there. And same way the other way. I'm going to go 4, 5, 6.5. So those are my foci. And they're always located inside the parabolas, you guys. Just like we did normal parabolas, the foci was on the inside. So I do have some students that make mistakes, and they'll put a focus point way up here. So that is definitely not right, because it's got to be inside the parabola. So just make sure you're paying close attention to that. And we can actually give those ordered pairs too. So if I need to figure out what the foci ordered pairs are, I'll write it down here. those ordered pairs are going to be, what's the y value is just 0, but the x value of the foci, I went from 3 and I added radical 41, and I also started at 3 and subtracted radical 41, because remember you start counting from the center. So 3 plus or minus radical 41, comma, and the y value is just 0 for all of those. Okay? There is one other random thing that I could ask. It's weird that my writing's not moving here. Not sure what's going on there, sorry. There's one other thing that I could ask. Slopes of asymptotes. So the slopes of the asymptotes. So what I would do to figure out what that is, I mean, that's kind of the easy part actually. You start on the center, and how far up and over did we go to get to the corner? So we went up 5 and over 4, so that's a slope of 5 over 4. And to get to the other corner, you still went up 5, but we went left 4. So the slopes of both of those asymptotes are plus or minus, we went up 5 over 4. Okay, so that's just done by looking at the center and counting up and over to the corners. You know the slope is rise over run. So that was a lot, you guys. Hyperbolas are kind of confusing, but what I'm going to do now is do the second example, and then I'll answer your questions in class, all right? All right, so here we are in our last example. We are going to do our center the same way. Just keep in mind, you guys, that the y is first, so the h and the k are still with the x and the y, respectively. So the x value is going to be -1, and the y value is going to be 2. So that's why I said you have to be careful, is that since the y is first, that's always your k is with the y. So we're going to do -1, comma 2. So make sure to flip-flop those. The -1, 2 is right here. Let's go ahead and start graphing it just like we do an ellipse. So underneath the y value is 4, which means I'm going up and down 2. So be careful. Make sure you don't flip-flop those. You got to be paying real close attention. Underneath the x is 9, so that means left and right 3. And then remember, you don't make an ellipse out of it. You actually just make a little box. And then you're going to connect your corners of your box to make your asymptotes. So these are a little bit steeper. And we're going to go this way. Alright, and then which vertices am I going to use? Which parabolas am I going to graph? Well, since y is first, I'm going to use the y values here. So this is one of my vertices and this is another one. And then remember, the asymptotes just attract your graph towards it. So this is why I have a hyperbola that is up and down, and that's because the y value was listed first. Okay, so let's talk about what the vertices are. What are those y values? I have -1, comma 0, and I have -1, comma 4. So those are the two blue dots that I used. The transverse axis connects them. So again, that's this time it connects your blue dots. So that length is 4. The conjugate is the other one. So that length is 6. Let's do slopes of asymptotes. So again, you're starting at the center of the box and you're counting up 2 and right 3. You're also going up 2 and left 3. So that is plus or minus 2/3. That's the slopes of the asymptotes. Only other thing we have to do, you guys, is find the foci. And then we'll use some common sense to figure out those ordered pairs. Alright, so I'm going to do a squared plus b squared equals c squared. Remember, a squared is always first for the hyperbolas, even though it doesn't matter because you're adding. So I get c equals plus or minus radical 13. Okay, so from there, what's radical 13? That is between 3 and 4, right? So like 3.5. So I'm going to start at the center, and I'm going to count up 3.5 and down 3.5. So I'm going to put a focus point here, and that's always starting from the center, 1, 2, 3.5. So that's a focus point here. Remember, you're not putting any foci out here or out here, because that's not inside your hyperbola. So just beware of that. It always has to be on the inside of the parabolas. So now all we have to do is figure out what those ordered pairs are. Well, I'm pretty sure that the x value for both of those is -1. And then I started at the y value of 2, because that's where the center is. And then I went up radical 13 and down radical 13. So those are my foci. That's it, you guys. Kind of a confusing lesson again, but come to class with questions, and we'll get them answered and we'll get our worksheets finished. And that concludes the 4 shapes that are conics. We just got a little bit of equation writing and stuff to do. We have one more video lesson, and then it's test time, and then finals, and then summer. Thanks for listening. Have a great night.